Hey everybody, this is a continuation of our chem842 lecture on um, sort of drug likeness and chemical informatic tools. So we last time covered a lot of these top items, drug absorption, reviewed how drugs are absorbed into the GI tract, aqueous solubility, the concept of log P and C log P, polar surface area, and we also talked about these two um, ways to determine drug likeness, the Lipinski rule of 5 and the Weber rules. We're not going to review those, but we'll see them again in a different context in a second, because we're going to actually look at molecules and use computational tools to figure out if they obey or violate the Lipinski and Weber rules. I'm not going to review all of SMILES also, but we'll just do a quick recap of what it is, and then we're going to move on to this section on generation of 2D and 3D structures. So where did we leave off with SMILES? What is SMILES? SMILES is like a text-based representation of chemical structure. Now, it can be used for simple molecules or very complicated molecules with multiple rings, etc. And that's what makes it really convenient, because it's very general for representing chemical structure, right? So I'm going to quickly go through it. Yeah, SMILES was this idea which we talked about, where a chemical structure can be broken down into some letters that basically describe the connectivity, even for a crazy molecule like ciprofloxacin. And Wikipedia had a good page for that, etc. Let's keep going through what we saw last time. We did some different molecules, including like vanillin, and just kind of showing how it seems like a pretty general approach. And if you have chiral centers, the chiral centers are encoded with this little bracket terminology, and it's called isomeric SMILES. All right. We did this exercise of looking up molecules in the PubChem website, which allows us to find the SMILES, which is nice. If it's a known compound, you can quickly find the SMILES. And if you have the option of isomeric SMILES versus canonical SMILES, the isomeric SMILES always gives you the absolute chirality. We also did this exercise where we would draw molecules, and actually it would this cactus website would determine the SMILES for us, including with chirality. So this Notch 2, Notch 3 inhibitor from homework 3, we could actually generate isomeric SMILES with the chiral centers. This is a COVID-19 protease inhibitor. I think this is our next homework assignment, homework 4, that you guys are working on now. And that this is a pretty complicated structure. We didn't practice the drawing of this just because it's kind of a difficult molecule to draw. But I think this will be maybe we might come back to this on the next homework assignment. So I'd probably just give you the SMILES for that. Let's see, what else do we got? And then we also use that PubChem website to be able to search for SMILES strings. So we'd use a SMILES string, figure out what the molecule is. So I'll just kind of shows you the utility of SMILES. Okay, we did this all, and then next we're getting into generation of 2D and 3D structures. This one we have not finished, so this will be kind of our new material. Last time I did also show you how to take a screenshot, because that's something not everybody does regularly. But we did this already. So screenshots on a PC and a Mac. Okay. Okay, so we're ready for our next activity here. we're going to use some online tools to convert a SMILES string into a chemical structure. And we can do either 2D chemical structures or 3D chemical structures even, which is kind of cool. Why do we need to do this? Well, like, we're going to be using tools soon that create new SMILES strings, like doing a synthesis in the computer. So we need to see what the structure of our products is. And so there's a couple tools that we like to do this with. Okay, so we're going to use a set of tools that are maintained at UC Irvine, and they have a website. It's the ChemDB Chem Informatics portal, and it has a variety of tools. We'll use some of the other tools later, but one of the easy tools we're going to use is just generate a 2D chemical structure. All right. Okay, so let's try this out. That's the website, and I think you can also just Google UC Irvine Chemical Informatics Portal. That's probably the easiest way. UCI Chemical Informatics Portal, or use that URL, and it just comes up to this ChemDB link. Okay, so we're inside the portal now, and there's a variety of tools that we have access to, and they're all free, which is cool. We're going to use the top right one called SMI to depict, generate a 2D image from SMILES. So I'm going to click on that guy, and now it has a couple like just random molecules as for demonstration, and I can even click. I can generate images of those. And we'll see there's a phenol, and then I don't know if this is even a real molecule. It looks like a well, anyway, it's a doesn't look very stable to me. Except, yeah, these are just kind of silly example molecules. So what I'm going to do is I'm going to go to my PDF copy of the lecture notes, and I'm going to copy. Let's go back actually here. Sorry, back to the PowerPoint. Okay, so we're gonna try this on ritonavir, which is an HIV protease inhibitor. We're gonna take we're going to get the SMILES, and we're gonna see if we can generate a chemical structure for it. And here's the SMILES string. Interestingly, this is kind of funny. I'm gonna drag my PDF copy over. And if you copy this, I copy this string. Why is it being silly? Copy the string. Okay, now I have the string on the clipboard, and I'm gonna get over to that website, which is here. And if I paste it, something funny happens. I'm going to generate images. And I see that, oh, actually, it looks like there's two molecules, but that's not true. It's actually one molecule, and the problem is when I pasted it, it pasted a carriage return, so I have to delete that carriage return, and now it's actually one long SMILES string. So you have to watch out for that little silly thing. And if I generate images now, I can see, okay, there's one molecule. That's the full structure of ritonavir, the HIV drug. So that worked. Okay. Going back to the PowerPoint, I'll move this guy out. So that worked, and then I have that example pasted in here too. So it's pretty easy to turn a SMILES string into a two-dimensional chemical structure. All right. Okay, so what about a three-dimensional chemical structure? And it's useful to see how a molecule might appear and bind to a target. The three-dimensional chemical structures, though, can be complicated because there's multiple conformations, and so there's not always just a single conformation, and it may not be, if we determine a structure, it may not be energetically minimum. But anyway, we're going to use a different tool, this mole inspiration tool, for 3D structure generation now. So this is not available on the UC Irvine website, which is fine. We're going to do an example of vancomycin, which is one of these crazy antibiotics for drug-resistant bacteria. So we're going to get the isomeric smiles. I did that already from PubChem. Actually, maybe we'll go get it just for practice. Okay, that's the two-dimensional structure of it. It's a big, crazy molecule with a lot of chirality. This is the string, and it's actually I could get it out of my PDF, but let's go Google it out of PubChem. So I'll go do that real quick. PubChem, vancomycin. Okay, so it actually has the smiles right up top, and I'm going to get it. And okay, so let's try this. Okay, so I have the smiles string now, and I am going to try this mole inspiration website. Got it on the clipboard. So let's go to mole inspiration. Okay. I can just Google mole inspiration. And there's this thing called the Galaxy 3D structure generator. And I'm going to click on that. And I'm just going to paste in the smile string and hit generate 3D. Takes a second because the molecule is a little complicated, but that's actually that came out with the 3D structure of vancomycin. Okay. Now there's other ways to view it, and sometimes they're a little easier to view it. So I can try like tubes. I like tubes. This kind of shows sort of a normal chemical bonding model. Okay, but yeah, we have to be a little cautious to understand if this really is an accurate 3D structure. It is generated pretty quickly. If you really need a good 3D structure of a small molecule, we often use tools like Spartan, or that's probably the one I would probably go to, and I think we have a license for that at SF State. Anyway, so with this, you can actually create a sort of cartoon 3D structure of a molecule. Okay. Okay, so next we are going to go back to these drug likeness models, the Lipinski model and the Weber model, and we're going to see if we can can predict these properties of drug likeness and oral bioavailability using computational tools. We haven't done that yet. Earlier we did learn about what the rules are, and we'll review those rules in a second also. But let's see if we can, and remember that the tools depend on parameters, right? They're called chemical informatic parameters, or physicochemical parameters. And so how do we determine those parameters? So we're going to do that with some computational tools now. Okay. So we're going to predict the Lipinski and Weber properties, the properties they use for their models. Currently, the only tool that I could find that does this that's free is the Mole Inspiration website, which is fine, and it's a nice website. It's hosted in Europe somewhere, but the tool works very fast for us. There's a slight annoyance with this tool though, and it used to not be this way, but we can't directly go from smiles to generate these parameters. So we have to do it a little indirectly. We have to go from smiles to something called a mole file, and then we can do that. It's just another step, and we'll do it. We'll practice it. So let's see what I'm talking about. And also, I found a great tool for that purpose. From going from smiles to a mole file, you just copy and paste it from one tool to another, and then you get the mole file, and then we can go from there. Okay, so we have a workflow, and it's going to be start with a smiles string, use this AAT bio website, which creates a mole file, and we can paste the mole file directly into Mole Inspiration. So it's just a little bit of copying and pasting and stuff. All right, so let's see how that works. Okay, so let's try this now with the Mole Inspiration tool. So we're going to try a couple different classes of molecules for this exercise. So we're going to use known orally available drugs. So that's a good test case. And we're also going to use some preclinical pharmaceutical candidates. So these are not, these are maybe halfway to a commercial drug, or even less, more likely less. So and these may have liabilities, or like there may not be orally available. And we'll also try a peptide-like pharmaceutical, which you probably can guess if that's going to be an orally available drug, or predicted that way with these tools. And usually the answer is no. So we'll see how that works out. Okay, so let's get going on some examples now. So again, the workflow, we're going to go from smiles to a mole file using the AAT bio tool. We'll show how to do that, and we're going to paste that into the Mole Inspiration tool. Okay. So we're going to do some known oral pharmaceuticals first. This is a reminder of what the Lipinski rule of 5 says, and also what the Weber rules say for drug likeness. And these parameters are calculated for us, so that is easy. Again, HBD is hydrogen bond donors. Oxygens and nitrogens, actually with a hydrogen usually. It's got to be less than or equal to 5. Hydrogen bond acceptors have to be less than or equal to 10. So those are usually just oxygens and nitrogens. Molecular weight needs to be less than 500. C log P, which is a measure of aqueous solubility, that has to be less than or equal to 5. And according to these rules, 1 violation is allowed. And then there's also the Weber rules, which is a different style of rules, and this says rotatable bonds are less than or equal to 10. Polar surface area is less than or equal to 140, and then no violations are allowed. Okay, so let's see if we can do this now. So we're going to start with warfarin, which is a anti-blood clotting medication used for stroke victims, and also people with like embolisms and clotting conditions. It's a known orally available drug, so we can anticipate this one will check out. And it has an expected, it's known to be 100% orally available. So let's see if we can validate that using these tools. All right, so I can get this string out of the PDF. I'll do that on my other window. Okay, so I have a copy of the string, the warfarin smiles. And I now need to do convert it to a mole file, and I'm going to use this AAT Bio website. So let me show you how to do that. That's easy. Okay, so I'm going to Google AAT Bio smiles to mole. So that brings it right up, and it's right here, the smiles to mole converter, the first one or second one. And it's really simple. We just paste. We can either upload a smiles file, but we can just go to option B, which is paste the smiles structure, smiles file, smiles string directly in there. There it is. And then it instantly creates a mole file and the results. I can just copy the whole thing, or just right click, select all, and copy. So now I have the mole file on my clipboard. And what do we do next? We're gonna have to go to the mole inspiration website, which we used earlier. So I can just Google that, +, mole inspiration, and right back to this tool. This is where we previously generated a 3-dimensional chemical structure, but we are going to try calculation of molecular properties now up top on the left. Okay, so previously you could paste a smiles string in here, but that doesn't work anymore, and I don't know why. And this, actually, this is warfarin, but let's paste it in from scratch. I just tried this a second ago without it recording. I'm going to try the white button. Okay, clear it. So how do I paste that mole structure in that I copied? I go to the smiley face, and I right click, and I hit paste mole or SDF. Now you need a right click button, or like a mouse, or maybe on your mouse pad on your computer, your tablet, or laptop. You can do this. On a normal tablet, I don't know. Pretty sure an Android tablet can't do this. I don't know anything about the Apple tablets. But anyway, I'm gonna do smiley face, paste mole file, and so now I can paste in that mole file that I created with the AAT Bio website, and I'm gonna hit accept, and now it came up. So there it is. That's the same molecule, right? Warfarin. There it is. Okay. So now I can do calculate properties, and it'll actually generate these chemical properties for this molecule, and then we can see how they compare with the Lipinski rules and the Weber rules. Okay, so let's see. Let's go down the list. Hydrogen bond donors less than or equal to 5. Where is this here? Well, that would be the number of oxygens and nitrogens, and that is 4. So does it match? Yes, it does, because it's under 5. What about hydrogen bond? Oh, I got it backwards. Sorry. For donors is actually this next one, number of oxygens and nitrogens with the hydrogens on them, and there's only 1, but that also matches the top rule, hydrogen bond donors. Okay, and then hydrogen bond acceptors should be less than or equal to 10. So that's this one with 4, and that totally matches. What about the molecular weight? The molecular weight's right here, 300, and it is under 500, so that matches. So everything's matching. That's cool. C log P. So the molar inspiration has their own way of doing C log P. It's called mi log P, mi log P, for mole inspiration, and it's at 3.03. So that actually is under 5, and so it basically all of these properties were consistent with the Lipinski rules. Okay, What about the Weber rules? Rotatable bonds it has here. So it has its own way of calculating these, and it's at 4, and that matches the Weber rules. And polar surface area is the TPSA, and that matches also. So it basically obeys all the Lipinski rules and the Weber rules perfectly, and so that would be not too surprising that it has perfect 100% oral bioavailability. It's absorbed very effectively and useful. Well, it's a good oral drug. Okay. All right. So next drug, sulfamethoxazole. We know what those are. Hopefully, if you remember, it's a sulfa drug. So these are class of antibiotics. There's a SMILES string. Let's try the tool and make a prediction and see how it compares with these rules. Okay, so I'm going to go to my PDF copy, and I'm going to get a copy of that SMILES string onto my clipboard. And now we have to go get the mol file, so I'll do that. I'll just go back to the AAT Bio website, delete the previous SMILES, paste the new SMILES. I think it just automatically did it. And then I will go copy the whole thing. It's select all, copy. Okay, and now I'm going to go back into mol inspiration, and I'm going to go back and I'm going to go into the drawing program. And I'm going to do the smiley face, right click, paste mol or SDF. And I'm going to paste that new one in and see what happens. There it is. Okay, there's our sulfa drug, sulfamethoxazole. Okay, so now I'm going to calculate the properties and see how they compare with the Lipinski and the Weber rules. Calculate properties. Okay. Now I'm going to move down and I can look at the rules. Okay, so let's see if these things match. All right. Hydrogen bond donors less than or equal to 5. So that would be the NO and H1 as less as 3. So that matches. The hydrogen bond acceptors less than or equal to 10, so it's 6. That matches. That's good. Molecular weight less than or equal to 500, and it does. That's a 253. And then the C log P is less than or equal to 5, which is my log P, and it is. So that in that case, all the Lipinski rules are obeyed. Let's check the Weber. Rotatable bonds is the N-rot B, and it's 3. Good. And the TPSA is 98, and it should be under 140. So it seems like all of the rules are obeyed. And I have the oral availability now, and this one is about 85%. So anyway, this is just another example of a known oral drug that basically follows all the rules. Okay, so let's actually try Lipitor now. I'm cutting to the chase. We'll see the oral bioavailability is less. It's around 12%. So this is maybe a bad well, we'll see what happens. Let's check out these rules. Okay, so I got to get this big long SMILES string on my clipboard. I'm going to go to the PDF on my computer, and I'm going to copy that big long SMILES string. So now I have the SMILES string. And let's go to the AAT Bio website, or web browser, AAT Bio. There it is. And I have to paste the SMILES up in the top right area. Paste. Okay, there it is. And then it created the mol file automatically. copy it, go into the mole inspiration website, go back, clear this guy with the white box, go to the smiley face, right click, paste mole or SDF, and I'm going to paste that Lipitor structure. Okay, so now we have this. Now we can do the calculation of the properties and then see how they compare. And you might make a prediction that maybe this violates some of the rules, and we'll see. And that might explain its poor oral bioavailability. Okay, so it did paste in and it did create the properties, and let's take a look now for Lipitor. Okay, so hydrogen bond donors 4, which is okay. Hydrogen bond acceptors is 7, which is okay. So no problems yet. Molecular weight is actually high, so that's a violation of the Lipinski rules. C log P is actually also high. So we have 2 violations of Lipinski, the log P and the molecular weight. So that, well, that would probably explain somewhat the poor oral availability. Okay, and then for the Weber rules, rotatable bonds is 12. Okay, so that is violating the Weber rules. And the polar surface area is 111, so that's not in violation. But, you know, the Weber rules say no violations are allowed at all. Okay, but that, you know, well, obviously Lipitor is used orally as a as an anti-cholesterol drug, and it you know, just because it has poor oral bioavailability doesn't mean it's unusable. It's just that, you know, they have to modulate the dose properly, and a lot of it's just never even absorbed orally. Okay. So these are not like a deal breaker necessarily, but certainly different drugs have different oral bioavailability. Okay. All right, next. We're going to just try some more. Okay, there's the rules. These are a couple of these research compounds that we talked about earlier, I think in the last PowerPoint. These are this neuropeptide YY1 receptor antagonist. It's like a neurological drug target I'm not too familiar with. But we did have a couple compounds that had varying amounts of oral availability, as we discussed. All right, so this is the lead structure. Recall, it had poor potency, IC50 of 2 micromolar, but they considered it good bioavailability. We'll take a look at that one first and see if the known bioavailability matches the Lipinski and the Weber rules. So I'm going to get a copy of that one. Okay, let's do the same sequence then. Got the smile string ready to go. Go to the web, paste it into the AAT Bio website. Got the mole file. Let's go into the mole inspiration properties predictor. Right, white box, clear it. Smiley face. Paste the mole file. There it is. Accept it. Okay, there's the molecule. The matches. Looks like it matches. Yeah, it's drawn different orientation, but it's right. Parachloro, yeah, N-methyl. Okay, so let's calculate the properties and see now. Okay, so Lipinski. Donors less than 5, good. Acceptors less than 10, good. Molecular weight less than 500, good. Oh wait, where is it? There, sorry. Yeah, it's good. It's less than 500. C-log P, they use their mylog P, and that is 5.4. So that is a violation, but one violation is allowed. Weber rules, rotatable bonds less than 10, and that is the case. PSA is less than 140, and that's the case. So basically, both of the rules are obeyed. Let's try the other one now. This is their optimized structure, where they optimized potency, but then it destroyed their bioavailability. And so we'll see if that matches the rules. And so yeah, they went from 2 micromolar to 1 nanomolar. This is the string, the SMILES string. Let's go try it out. I'll get it on my clipboard. Okay, got the SMILES. Let's try it out. Back to SMILES to mole. Paste the SMILES. Get the mole. Go to mole inspiration. Go back. Clear it. Right click. Paste mole to SDF. Paste as mole. Accept. There's the molecule. Calculate the properties. Let's check the rules. Log, going from the top here, hydrogen bond donors is actually fine. Acceptors is actually fine. 6 is less than 10. Molecular weight is high, so that's a violation. Right? And C-log P is high. So it's 2 violations. We'd say that, this is a Lipinski violator. And then the Weber rules, rotatable bonds less than 10, and that's the N-rot B, and that is also a violation. And the polar surface area is not a violation. But because of the way we do this, with the amount of violations that are allowed, they're both violated and not. I mean, this compound is non-compliant with the Lipinski rules or the Weber rules. So it kind of makes sense that it has poor bioavailability. So yeah, I think the rules seem to be working. So that's nice for a couple of different molecules. All right, so. Okay, so let's keep going with this. This will be fun. I am going to try a peptide-like pharmaceutical. So hopefully you have a prediction on how good the availability is going to be. So first one we're going to do is vancomycin, which we saw the structure earlier. It's a crazy polycyclic molecule with a lot of chirality and just a pretty crazy structure. I can get this. I can get the string with my PDF file, but I just have to make sure that I delete all the carriage returns, and I'll just practice that. So I'm gonna copy this onto my clipboard, but it may have some carriage returns built into it. So, okay, I have the SMILES now. Let's try the tools. I'm going to go into the AAT bio, delete, wait, it said your input may not properly be formatted for SMILES. Yeah, it got confused with all those carriage returns. Maybe the best way to do this is I'll go get it from PubChem. So let's do that. PubChem. Go get it, fresh copy. Vancomycin. Here's a SMILES, let's get it. All right, there's a SMILES of vancomycin. Now I'm going to go into the AAT Bio website. I'm going to paste it, and now that actually, I think it did work. We'll see. We'll see if it worked. So now it's a huge mole file. Let's see. Select it. Select all. Copy the mole file. Go over to mole inspiration. Go back. clear it, right click on the smiley face, paste as mole or SDF, paste the big mole file. Let's see what happens. Does it work? Yeah, that looks like vancomycin. It's a little huge. I can't. This is the way this works. You can't really see the whole structure. It doesn't matter. We have it. I'm going to do calculate properties now. It is even to paste in. Okay. Let's see what we got. And that looks like vancomycin to me. It's a single molecule. So the smile is copied and everything. Let's take a look and look for violations. So hydrogen bond donors less than or equal to 5, and now that's there's 21. So that's a violation. That's a huge violation too. 21's a massive violation. Hydrogen bond acceptors should be less than or equal to 10, and it's 33. So that's a big violation. Molecular weight less than 500. Well, that's 1449. So that's a big violation. C log P is actually not a violation. This is the only non-violation. So total we have 3 violations, which is pretty extreme for Lipinski's rule. And then for Weber, let's see how Weber works here. Rotatable bonds less than or equal to 10, and there's 13. It calculates 13, and so that's a violation. Polar surface area is 530, which is in violation. So this the rules are properly arguing that this is a non-drug-like molecule, and it would make sense that maybe a poor bioavailability, and that's 5, and so vancomycin is one of these drugs that you would administer by IV because it's so poorly bioavailable, and maybe it could be used for a stomach infection or something if you I'm not sure if that's true or not, but like some drugs can be poorly bioavailable but used to treat conditions in the stomach. Let's do one more. Or Rita Vanson, and you might make a prediction that this is also probably a poorly bioavailable drug. Let's just double check, and I'm gonna probably go get this off PubChem2 because I think the smiles string is going to be a little funny when I copy it out of my PDF. So let's go over to PubChem again. Or Rita Vanson. I think there's also an antibiotic. Let's see. Semi-synthetic glycopeptide for acute bacterial skin and skin structure infections. So it is also an antibiotic, kind of like vancomycin. Maybe I'll just look for the PubChem down here. There's this. I'm sorry, the smiles. There's the smiles. Get it copied. Got the smiles. Let's go over to the AAT Bio website. Paste it. Get the mole file. Copy paste. Go to mole inspiration. Back. Clear. Right click. Paste the mole. And now I accept it, and there it is, and I can calculate the properties and see. So it's pretty similar to vancomycin, I think, in its properties, so probably not a big shocker that this is a poorly orally available drug. And actually, so donors, there are 22. Acceptors, there are 36. Molecular weight is 1793. C log P is actually not in violation, but still we have, and it actually calculates the violations right there. There's 3 of them. Rotatable bonds, that's a violation. PSA is also, so yeah, so both of the rules are completely violated, and so As expected, this is a very low, not established. It's administered IV, but also since it can treat skin infections, it could be just administered on the skin, I think. Definitely not an orally available drug. So I just took a quick look at the PubChem website, and it mentions that this Orita-Vancin is actually only really used as an IV formulation, even for skin infections, which is a little surprising to me, but maybe it's not even absorbed well into the skin. But anyway, so I don't think you can use it like topically. Okay, onward. We're moving out of the drug likeness prediction stuff and into prediction of metabolism. So we're going to review a little bit of the these phase 1 and phase 2 metabolism types, and look at some molecules, and they use computational tools to predict metabolism. Okay, let's see how that works out. And there's going to be a couple different tools. One of them just predicts the sites, like where in the molecule is it high probability to be metabolized. And there's another tool that actually predicts the structures, but they are actually two different tools. And remember what the difference between phase 1 and phase 2 metabolism is. Phase 1 is pretty much chemical modification, or addition of a functional group, a hydroxy group, or maybe cleavage of an amine or something. Phase 2 is the addition of a conjugating a molecule like glucuronic acid or something. Okay, so we're going to really use one server for all of this. There used to be a couple servers I liked, and it's nice that we can just kind of focus on one server now. And it's called the Nerd Server, New E-Resources for Drug Discovery. It's a collaboration between the University of Hamburg in Germany, University of Prague in Czech Republic, and University of Milano. I can't read that in Italian, but it's a cross-university collaborative project, and they have a nice website that works for metabolism prediction. So there's two tools. One's called FAME2. I think we actually use FAME3 now. They're using FAME3. This just predicts the sites of metabolism. So where in the molecule is metabolism likely? As it uses a variety of predictive tools based on the chemical structure. GloryX is their tool for predicting actual metabolite structure. So we use it. We're going to play around with both of those to show phase 1 and phase 2 metabolism. Okay, prediction of metabolism. So we're going to try out this Nerd Server. There's the link. Let's go get it. I'll get it off my PDF. Okay, open it up into a browser. Nerd Server. And we see a couple of the tools that they have developed. We're going to use FAME3 and GloryX, which are pretty good representative tools. Okay. And actually, so I guess we're going to use FAME3 for the sites of phase 1 metabolism. We're going to use FAME3 for the sites of phase 2 metabolism. And we're going to use GloryX, which predicts the structures of the phase 1 and phase 2 metabolites. Okay. So let's try the Nerd Server for using the FAME3 for phase 1 metabolism. And what's the molecule? Let's try this tricyclic antidepressant, norpramin. It's a selective serotonin reuptake inhibitor. Any predictions? Sites for phase 1 metabolism. Do you have any ideas where you might imagine metabolism to occur? And this is, you got to know some of the metabolism reactions we talked about before. So phase 1 metabolism is often oxidizing a functional group, or maybe cleavage of a methyl group, etc. So you might expect maybe oxidation of the nitrogen, maybe cleavage of the methyl, possibly oxidation of this site here, which might cause cleavage of the carbon-nitrogen bond. But those are the kind of things I think of phase 1 metabolism. Possibly, depending on the chemical structure, maybe oxidation of the aromatic ring. All right, so those are some predictions, my predictions. So let's see. Let's go get the smiles. I'll get it out of my PDF. Got it out of my PDF. Now we can paste this directly into this FAME3 website. So I'm going to go back to the nerd server. I'm going to hit the FAME3 button. And I'm going to go down and I'm going to paste in the smiles. Now, because we just want to do phase 1 metabolism, I'm going to go to this little tab and I'm going to deselect. I'm just going to select phase 1 metabolism. Okay. All right, let's submit it. From my recollection, this takes a little bit of maybe a minute or so. So I'm going to actually stop the recording and I'm going to come back with the result. So we don't have to both look at this little circly thing, and then I'll come back in a second. Okay, so I'm back after it finished. All right, so the way it presents this, and again, it's really just a probability at different atoms that metabolism might occur, and it pretty much matched our predictions. So the blue are a higher probability, and I think I agree that's probably the most likely metabolism site, is maybe demethylation. Remember, what happens with P450 is that it would hydroxylate the methyl, fall off to create formaldehyde, and then be cleaved, so to demethylate. And then the other one it predicts is maybe just direct oxidation of the nitrogen. Remember also that oxidation of the carbon would be cytochrome P450, while oxidation of the nitrogen would be FMO. So there's that was what we learned about in the metabolism lectures. Other ones, maybe 0.2 probability that this one would be hydroxylated. It would probably cleave off also. Anyway, it's pretty cool. This is a nice tool. So let's keep going. All right, so that's this decipramine. How about Xanax? This is a benzodiazepine, like a sedative drug. Any predictions on this one? So, I mean, I kind of think maybe the aromatic ring, like this unsubstituted aromatic ring. The chlorine one probably would not metabolism in my opinion, because the chlorine's also electron withdrawing, and I think it kind of protects this chlorine. We also have just like a methyl sticking out. That's a potential site of metabolism. Well, let's just go ahead and see what this website predicts. Here's our smiles. I'll go get it off my PowerPoint. The smiles of Xanax. Oops. Okay, got it. And now I'm gonna go back to the nerd server. Go back. Here it is. I'm going to go back one. We're on FAME3. Paste in the Xanax molecule. I'm going to reselect phase 1 metabolism. We'll do phase 2 in a second. Here's phase 1. Submit. It's going, and I think it's also going to take a little time, so I'm going to stop and come back after we have results. Alright, so here's the results for the Xanax phase 1 metabolism. It predicts with highest probability that this carbon would be oxidized. And it kind of makes sense because it is next door to like a heteroaromatic ring system, and that would stabilize a radical potentially, and so you know, that would maybe lead to favorable oxidation here. It's not sorted by probability, which is a little weird. So if you go down a bit, you see, oh, the C16 is maybe oxidized. This is actually the same kind of rationale. I think it's next to this heterocycle, next to the nitrogen, and that may stabilize that and maybe increase the probability. Otherwise, there's not a ton of predicted metabolism. Slightly higher than 0 metabolism is a C20, which is actually kind of what I predict also. Unsubstituted phenyl would be a reasonable site of metabolism. So hydroxylation or something. That's a very, like we mentioned that when we talked about metabolism also. All right, so let's see, anything else to see for this one? No. Okay, so let's go to the next one. Stop recording. All right, next we're going to go to the phase 2 metabolism, the sites of phase 2 metabolism utility. So this is FAME3 also, but we're going to specifically select the phase 2 metabolism option. So let's go back to dicipramine, this tricyclic antidepressant. Any predictions for phase 2 metabolism? What do you think? You know, maybe a site where a phase 2 the conjugating group might attach. And I mean, looking at it, really, you know, the only sites would potentially be the nitrogen. I don't think the other nitrogen could really be a site. So I think it's just it's a reactive secondary amine nucleophile. I think that's a pretty reasonable prediction that I would make. Let's see what happens. So I'm gonna go get this smile string. Okay. So I selected it. Let's go to back to FAME3 on the nerd server. Go back, paste, select phase 2 metabolism. So now we're in phase 2 metabolism versus phase 1 metabolism. Submit. And I think it's going to take a bit, so I'm going to stop and come back. Okay. Okay, so it, I think it successfully logically argues that the nitrogen would be the place that a conjugating group would go. Now, it doesn't show that because that's the other tool, GloryX. We'll be doing that one in a second. But I think that makes sense. There's really the only site of a potential phase 2 conjugation event would be on the nitrogen. All right, so next. Now we're considering atenolol, which is a beta blocker. I want to use like maybe a hypertension drug or something like that. So I don't know. What do you think for phase 2 metabolism? Places that a conjugating group might attach. Looking for nucleophilic atoms. I mean, I think the obvious ones would be maybe the alcohol, maybe the secondary amine, potentially this nitrogen, although it's not totally nucleophilic. But I think amides are still reactive. Those are probably the most logical places that you could conjugate glucuronic acid or an amino acid or something like that. So let's try it out. There's the smiles. Let's go get it. I'll go get it. You can try getting it if you want. Also, go back to the nerd server, go back. I'm going to go to the prediction part, go to phase 2 metabolism, say paste to smiles, set it to phase 2, submit. It's going. I'll stop and come back when it's done. Okay, it's done with this beta blocker drug, and it's if we look at all the numbers and sort of the higher probability ones, it's saying the alcohol is probably a higher probability, and then a second it would be the amide, which is a little surprising, but I maybe think this secondary amine might be a little more, and it is up there, but a little lower probability. It might be due to sterics of this isopropyl group. I don't know. That's possible. This has a little less steric hindrance. Okay, moving forward. Done with tenolol. Kind of made sense. So what we're going to do next is we're going to try this tool called GloryX, also on the nerd server, and we're going to predict phase 1 metabolites. So this will actually predict the actual transformations, which is definitely helpful in medicinal chemistry. Now this, I don't know, what do you think for phase 1 metabolism? I would kind of imagine maybe oxidation of the nitrogen, or maybe dealkylation of the methyl, so hydroxylation followed by cleavage to make formaldehyde, all the kind of stuff we did before for metabolism. Potentially dealkylation of this, potentially hydroxylation of a phenyl. These are all options. Let's try it out. And so I'm going to get the smiles string again, but we're going to use a different tool then. So I'm going to go to my PDF file, get the smiles. I have the smiles. Let's go back to this nerd server, go back one, go back another. This is the main toolkit, and I'm going to go to GloryX, which is metabolite structure prediction for phase 1 and 2 metabolism. I think GloryX is actually used for human metabolism too, specifically. So it's fine-tuned for human, whereas I think the other one might work for mice or non-humans. Okay, let's go GloryX. So it's the same kind of thing, and we can just paste in our drug. We're back to what are we doing? We're doing the disipramine again, yeah, the tricyclic drug, yeah, and I'm going to set it to be phase 1 metabolism on the GloryX tool. Submit. Not sure how long this one's going to take, but I'm just going to stop it and come back. So here we go. I'm going to stop the recording. Okay, so GloryX is done now, and we're on this molecule. So it has it kind of sorts conveniently by like a priority score, sort of a probability score. The first thing, so we can kind of click each of these options. First one is kind of what we might predict, demethylation. So it predicted that the methyl group would get hydroxylated, but that always falls off to make formaldehyde, and that would make the primary amine, so that makes sense. It also predicted maybe amine hydroxylation, which we said would be the FMO. This is probably P450 mediated, FMO mediated. This dealkylation, I'm not exactly sure how this occurred, and I have to think about it, but conversion of the amine to a hydroxy group. The next one is the aldehyde. That one actually makes more sense to me, where, how would that happen, dealkylation, if this side would hydroxylate, and then it would make an alcohol, and it would kick in and break off and make an aldehyde. So that's actually pretty logical. This intermediate is actually kind of midway to the dealkylation at the top, which because it forms this, then it breaks off and makes formaldehyde. And then it just kind of goes down, and there's some other ones like maybe the tertiary amine hydroxylation. I think these are lower scores. I kind of focus on the top ones, but there are some, I don't know, like lower where it shows the aromatic hydroxylation. Apparently, it's pretty low probability for these antidepressants, etc. So let's just keep going. And I think when if we ask for this on homework, I'll tell you what kind of ones I want. Usually a couple of the high priority metabolites. All right. Next one is atenolol. This is back to our beta blocker drug. Let's do some potential phase 1 metabolites and make some predictions. I would probably predict that maybe the isopropyl would fall off, hydroxylation followed by kickoff and make a dealkylated thing. It would make acetone, like this would fall off as acetone. Potentially oxidation of the alcohol to a ketone. Maybe cleavage of this group off. Potentially oxidation of the CH2. All these things are possible. I mean, this has a lot of positions next to a benzene or next to a heteroatom. Those are a couple predictions. Let's just go for it and see what happens. I'm going to go to my PDF, get the molecule. I'm going to go back to the nerd server. I'm going to go back. I'm GloriaX, paste, phase 1 metabolism that we're doing. Submit. Maybe I'll stop real quick. Let's see. Oh, okay, it went fast. Never mind. Okay, so let's see. Let's take a look. It's saying? The numbers are not as high, so maybe it's not as optimistic. Hydrolysis of the primary amide. So that makes sense that the amide would hydrolyze. Is one of them. Benzylic hydroxylation. Like we said, maybe hydroxylation of the site next to the benzene. Amine hydroxylation. What's going on there? That's interesting. Maybe. Well, it's a prediction, but it is saying that the amide nitrogen could hydroxylate. That is actually a known functional group, so that's maybe not too crazy. This is just showing, I guess, if that fell off. Let's keep going a bit more. Aliphatic hydroxylation. So dealkylation of I guess this piece, if it hydroxylates, kicks off, makes an aldehyde. Hydroxylate. The hydroxyl kicks off the amine. It would be make an aldehyde. That's what it's saying there, I guess. Or there. That's what it's saying there. Dealkylation. That's the one I was kind of predicting. Maybe. A couple other options, but they're lower probability. Yeah, but anyway, this is a nice tool. It's a prediction for drug these metabolism reactions. I think we're going to keep going. Let's go next one. Now we're going to do phase 2 metabolism predictions. So this is going to predict maybe conjugating groups that could be attached and the structures of them. That's kind of fun. It's a little different than phase 1. Okay, this attaches, glucuronic acid sulfate to enhance drug excretion. Let's do it. Okay, so now we're going to consider, so this is a 4-hydroxytamoxifen, so it's a breast cancer drug, and this molecule undergoes phase 1 metabolism to the 4-hydroxy, And so let's look at the phase 2 metabolism of the 4-hydroxy molecule. And I have that. And what's any predictions? I mean, the obvious prediction is, well, you got a nucleophile, maybe you would get attached with some kind of conjugating group. So that's not well, that's a reasonable prediction. These atoms can't really attach stuff, so I'm going to put all my prediction into the conjugation of the hydroxy group. So there we go. There's the smiles. I can go get it for my PDF. All right, I'm going to get the nerd server back. Go back. Phase two metabolism only. Submit. Let's see, I think this one goes fast. Faster. Let's see. Well, I'll stop it and come back. Stop. All right, it says back. And kind of, there's the molecule, sort of as expected. It's predicting phase 2 off the 4-hydroxy group, so glucuronidation, high probability, and also it's predicting sulfonation, so that's anticipated. What else is it saying? And glucuronidation. So that's interesting. I'm not sure if well, I mean, maybe it's reasonable, but I mean, it's making a quaternary ammonium, and I don't know how likely that is with glucuronidation. The top two I think make the most sense, and then methylation is another option, and we know that to be true, but it's actually lower probability. So I would say the top two are the ones that I would actually probably predict myself. The third one is an interesting structure because of the quaternary ammonium. Fourth one, we know is methylation not happening very much, so not too surprising. Okay. Let's take a look at the next example. This is a steroid. It's an antibiotic, a steroidal antibiotic. Fusidic acid. Any predictions? Really looking for the nucleophilic functional groups, and I mean, I'd say the alcohols, glucuronidation or sulfonation, maybe something to the carboxylic acid, maybe an amino acid conjugation event like a glycine or a glutamic acid, because we learned those too. Those are my predictions. Really looking for nucleophilic atoms and thinking about the things that could happen to them. Let's take a look. Here's the smiles, big long smiles. Probably gonna have, let's see if I can get the whole thing. I copied it. It's a big long smiles. There may be a carriage return at the end, so I may have to delete the carriage return. Go back to Fame. Gloriex. Go back. I'm going to paste in, but I'm going to make sure that there's no carriage return. So I'm going to go to the end, delete, and see what, I think that I have to do that. Otherwise, it may be confused. It might still be confused. So phase 2, let's see if it draws the structure correctly and see if it has a prediction. Submit. I'll let it go. I think that... I guess I'll stop, come back. Stop. Okay, it's back. All right, let's take a look. Yeah, it's got several of these higher priority predictions. The highest priority is sulfonation of one of the kind of terminal. This probably is this hydroxy group on the steroid, and then next is glucuronidation of the same hydroxyl. It's just oriented funny. So, because you have to look at this is getting rotated a bit, but it looks like this hydroxyl group is getting either sulfonated or glucuronidated. And so in this one, sulfonation, glucuronidation, and going down in probability. it's actually predicting glucuronidation of the carboxylic acid, which does actually happen. Lower probability, and then maybe the other alcohol, which is this alcohol, which this other alcohol is a little more sterically hindered. So it kind of makes sense that the one that's kind of poking out would be the one that is the most reactive. Sulfonation, glycination. There we go. Yeah, that's lower probability, but you can imagine it's making a prediction that the glycine is being attached to the carboxylic acid. And then glutathione. Oh, glutathione, really? Where's glutathione? It is apparent there. Oh, that's interesting. Yeah, glutathione, which of course is the nucleophilic. I can't download it, can I? Nucleophilic scavenger. It's a thiol, so it's attached. It's sort of doing a. It looks like a. I can't. I wish I could download it. Can I make it bigger? I can't easily get it. I think it's doing a Michael reaction type thing. The sulfur of the glutathione is attacking. I would imagine it's this position because it's a Michael reaction off the neighboring carboxylic acid. So that's that's electrophilic position. Sulfur would attack the electrophilic position. It's low probability, and I think it's sterically hindered, but I think that's what it's trying to say there. So that's cool. All right, so yeah, and this, I think I made this note that maybe glycine or glutamine conjugation to the acid. I think with the earlier version of Glory, it didn't show that, but this newer version of Glory, the Glory X tool, it did actually predict glycine or glutamine conjugation. So that's cool. I mean, I think it's a useful tool, especially if you have a molecule where you're not too sure where the metabolism might be. It's also a useful tool for maybe some scientists that don't know organic chemistry as well to make a prediction on metabolite structure. Organic chemists, I think we understand nucleophiles and electrophiles maybe pretty well. I still think a tool like this is useful if you're trying to figure out what your metabolite structures are, if you're using mass spec or HPLC or something. Okay, I think we're done with that part. We're going onward to virtual screening in silico synthesis, homology modeling, docking, and molecular dynamics. I'm going to try to go into a little bit of this now. We may bump this a little bit to the next time also. Okay. All right. I thought about going onward now, but this might be a good time to stop. And I do have a little bit more stuff I think that's good for an asynchronous video lecture, but I'm going to wait on that and maybe a couple days. So I will record one more video. I think we're going to return to our in-person teaching next week also, because the last little bit of this I can do in person just as fine, and then we have some more PowerPoint stuff that's all really good in person, prodrugs, and then I think eventually antibody drug conjugates and some other really fun things. So as of now, I'm going to stop this video presentation, and then we'll have one more video that you'll just watch when you get a chance. And then I'll also, I think next week will just be normal in person till the end of the course. Okay, have a great night or day, depending on when you're watching this. Take care.